Hello ICRC 2023. My name is Owen Hoffand. I'm a PhD student from the University of Michigan where I study under my advisor John Hayes. Today I'll be presenting a paper titled Mitigating the Correlation Problem in Multilayer Stochastic Circuits. I regretfully am unable to attend the conference in person because I am currently sick with COVID. However, I am thankful to the ICRC staff for providing me with an alternative presentation format. For this talk, I will begin by giving a brief introduction to the field of stochastic computing for those of you who may be unfamiliar with the topic. Then, I'll define the correlation maximization problem and an algorithm we've developed called COMAX that solves it. Finally, I'll present a case study of applying COMAX to a representative image processing circuit, showing how the algorithm can be used to achieve performance improvements in practical SC design scenarios. So, without further ado, let's begin with a background on stochastic computing. For those of you who may be unfamiliar, stochastic computing is an unconventional and approximate computing paradigm that encodes data within sequences of ones and zeros known as bit streams, instead of using binary. A stochastic number x is a sequence of n zeros or ones with a value represented by px, the probability that any bit of x is 1. A typical SC system will begin with a binary to stochastic converter, or BSC, which converts the fixed point binary inputs into stochastic bit streams with the specified probability values. These BSCs usually contain hardware implementing a pseudo-random number generator as the source of randomness. Next, the SC core logic operates on these bit streams to compute functions of the probability values. And finally, a stochastic to binary converter, or SBC, samples the output bit streams, converting them back into binary. Circuits operating using stochastic numbers instead of binary tend to achieve better area and fault tolerance at the cost of lower precision and higher latency. For instance, a single AND gate multiplies the input probability values when the input bit streams are uncorrelated. Compared with a conventional multiplication circuit based on binary addition, the stochastic AND gate multiplier has substantially lower area. The table on this slide shows a few other small circuits that implement useful functions efficiently in SC. In particular, the MUX gate achieves a very useful scaled addition operation. Observe also that each Boolean logic function is associated with a stochastic function. This distinction makes SC circuit design versatile yet challenging, as it's possible for multiple different Boolean logic functions to achieve the same stochastic function. There are many exciting applications that are currently being explored by the stochastic computing research community. Here, we've highlighted two that are particularly relevant to our current research. The first is an example of a near-sensor stochastic edge detection circuit constructed using no more than 3 logic gates. It is able to produce convincing edges after only a handful of clock cycles, making it extremely power and area efficient, ideal for battery-constrained image processing environments such as mobile cameras or drones. The second application is a finite impulse response, or FIR, filter, implemented using a MUX tree architecture known as CMUX, shown here applied to a FIR filter for an electrocardiogram signal denoising task. Both of these applications require their inputs to be correlated in order to achieve the best accuracy. Next, we discuss how bitstream correlation impacts the behavior of stochastic circuits and define the correlation maximization problem, which our work seeks to solve. In SC, bitwise correlation between a pair of bit streams is defined by the likelihood of encountering overlapping ones relative to the values of the two bit streams. For example, here we see 3 cases in which a pair of bit streams x and y with probability values 6/10 and 5/10 respectively are either fully correlated, uncorrelated, or anti-correlated. The overlapping ones are highlighted in red, and the corresponding overlap probability is shown. In SC research, correlation is typically measured using the stochastic cross-correlation, or SCC. With this measure, SCC equals 0 is assigned to the uncorrelated case, and SCC equals plus or minus 1 is assigned to the fully correlated and anti-correlated cases, respectively. A simplified version of the SCC equation is shown. It relates correlation to the bitstream values and overlap probability. Correlation presents a problem in stochastic circuit design because the stochastic function computed for a given logic function changes depending on the SCC of the inputs. For example, here we see a small AND gate circuit which computes the function px times 1 minus py when its inputs are uncorrelated with SCC equals 0. On the other hand, when the circuit's inputs have maximum correlation, this same circuit computes an entirely different function, this being a saturating subtraction function. To visualize the effect that this correlation change has on the circuit's function, this graph plots the function's output z versus the x input probability, assuming that the probability of the y input is 0.5, for several different SCC values. Many practical designs, such as the edge detection and digital filtering circuits we saw earlier, require their inputs to have SCC equals 1. In this graph, if we assume that the green SCC equals 1 curve is the desired stochastic function, then other SCC values will cause the output function to be incorrect. The central problem of this work is maximizing the expected SCC during the design phase in order to minimize these correlation errors. For example, increasing the SCC from SCC equals 0 to SCC equals 0.37 to 0.86 and finally to SCC equals 1 gradually produces better approximations of the target stochastic function. Thus, a higher SCC leads to lower correlation error. While correlation can be controlled at the primary input to a stochastic circuit, it is not known how to control the correlation at the output of a circuit. This is a problem for stochastic circuit design because circuits can be composed of two or more layers of logic. For example, let C1 and C2 define arbitrary stochastic circuits. Then, the output SCC of layer C1 is not controlled, and thus C2 may have a significant amount of correlation error. The typical method of fixing this problem is by inserting a sequential correlation correction circuit S1 between circuits C1 and C2. The most straightforward implementation of a sequential correlation corrector is to completely regenerate the stochastic bit streams with the exact desired correlation value. However, this is very costly in terms of both circuit area and latency. There are several papers that explore the topic of sequential correlation correctors that only approximate the target SCC value. However, while smaller and faster than full regeneration, these designs still add large area cost. Instead, our work is the first to introduce a systematic way of directly redesigning the existing C1 layer to improve its output correlation without adding any extra sequential hardware. The goal of our work is to maximize the output SCC of C1 while keeping the stochastic function which C1 computes the same, a condition called stochastic equivalence, or SE. This is possible because, as we mentioned earlier, it's possible for multiple different Boolean logic functions to achieve the same stochastic function. As it turns out, two stochastically equivalent Boolean functions can have wildly different output correlations. Formally, then, let f of x and f star of x be stochastically equivalent Boolean functions with n inputs and k outputs. Then f star solves the correlation maximization problem if it maximizes the SCC between all pairs of outputs for all possible inputs x. Note that solving the CMP does not necessarily guarantee that SCC equals 1. Instead, out of all possible implementations of the desired stochastic function, the CMP solution is the one that has the highest SCC. Next, we present an algorithm called COMAX that solves the correlation maximization problem in the general case. Suppose we are given as input to our algorithm an array of Boolean truth tables that define the logic function f, expressed as binary vectors. Our COMAX algorithm simply returns a new set of Boolean truth tables representing a solution to the CMP. For example, this mux-based adder has 3 inputs and 1 output, so the truth table is just a single binary vector of 8 entries. Now we remark that the inputs to SC circuits generally fall into 2 categories. The first are constant inputs, which come from the random number sources within the stochastic to binary converters. All of these have the probability value of 0.5. It is well known how to construct other constant probability values by performing logical operations on multiple such 0.5 valued constants. For example, 0.25 can be achieved by multiplying 0.5 by 0.5. The other type of input are variable inputs, which includes inputs from the binary domain or inputs from prior layers of SD computation. Variable inputs may have any probability value. Let NC and NV equal the number of constant and variable inputs, respectively. For example, the mux-based adder has 2 variable inputs, x and y, and 1 constant input for the select, s, so the NV is 2 and the NC is 1. The next step of COMAX is to reshape each of the input truth tables from a 2 to the n by 1 binary vector into a 2 to the nv by 2 to the nc matrix known as a stochastic equivalence matrix, or SEM. This reshape is done so that the rows represent variable inputs and the columns represent constant inputs. Due to the fact that columns represent constant inputs, observe that each column of the SEM has an equal chance of affecting the circuit's output for a given input pattern. This gives rise to a desirable property about SEMs. The stochastic function does not change as long as the number of ones in each row stays the same. In other words, SEMs f and f star represent the same stochastic function if their row-wise sums are the same, as shown in the equation on the right. Using the mux example from earlier, the row-wise sums produce a vector containing 0, 1, 1, and 2. COMAX takes advantage of the fact that row-wise permutations do not change the overall sum, and therefore they allow us to modify the circuit's Boolean logic function without changing the circuit's stochastic function. In other words, the new circuits remain stochastically equivalent. In particular, COMAX arranges the ones in each row of the SEM such that they are all aligned starting from the left side of the matrix. Our paper proves that this solution solves the correlation maximization problem by maximizing the number of possible alignments of ones at the circuit output. From here, the final step is just to reshape the modified SEMs back into the binary vectors. Here, it's done for the mux circuit. The resulting Boolean logic function is shown. This is the logic function describing a type of logic gate called a majority gate. Prior work has shown that majority gates and muxes both perform the scaled addition stochastic function, and that majority circuits tend to have higher output correlation than mux ones. By applying COMAX here, we've actually proven now that majority gates have the highest output correlation among all possible 2-input scaled adder circuits. As a larger example, consider the following two SEMs, which represent the two output circuits shown on the right. Here we show how COMAX aligns the ones to the left side of the SEMs and the resulting circuit it produces. Notice how the optimized circuit, after simplification, actually uses one fewer constant input, showing that COMAX can automatically discover creative design ideas that increase correlation. We now show a larger scaled case study of COMAX being applied to a representative SC image processing circuit. The following figure is a block diagram of a 2-layer SC image processing pipeline consisting of a 3x3 Gaussian blur circuit followed by an edge detector circuit. The edge detector implementation requires its inputs to have SEC equals 1, i.e. maximum correlation. This case study was chosen because it has been used in several existing SC works on sequential recorrelation circuits, making for a good comparison with COMAX. The first layer, C1, implements a 3x3 Gaussian blur function, which computes the equation shown here. Our circuit accepts a 4x4 image tile, so we have 4 copies of the relatively small SC implementation, one for each possible placement of the 3x3 kernel. The second layer is the 3-gate Roberts cross edge detector that we discussed earlier. Its efficient 3-gate implementation requires the input SEC to be equal to 1. When both layers are combined, we call the full circuit GB plus ED, Gaussian blur plus edge detection. To test the full circuit, we used 10 test images from the MATLAB image processing toolbox with added Gaussian noise. Each image was broken up into many 4x4 windows and then fed into the GB plus ED to circuit, simulated using bit streams of length 256, both before and after applying COMAX to the first layer. For comparison, we simulated the effects of adding additional sequential recorrelators between layers 1 and 2, as shown in the figure here. To evaluate how COMAX impacts the average output SCC of the Gaussian blur layer, we measured the output SCC for every placement of the 4x4 kernel within the test images. The plot shown here is a histogram showing the relative frequency at which different SCC values are produced. The blue and orange bars represent the performance before and after applying COMAX, respectively. It is clear from the orange bars that applying COMAX to the circuit causes the output SCC to be more consistently concentrated in the range of 0.93 to 1, compared to the blue bars, which show a significant number of SEC measurements at lower ranges, including SEC equals 0. These results are reflected in the averages, which show that COMAX increases the average SEC from 0.72 all the way to 0.97. Next, we show an example of COMAX's performance in terms of image quality. On the left, we see one of the test images with its added Gaussian noise. In the middle, we see what this filter design can achieve in terms of noise reduction and edge detection when implemented using floating point arithmetic. Finally, on the right, the result showing the output of the SC circuit without COMAX is shown, showing how the unoptimized design performs poorly because of the lack of correlation control. In contrast, after applying COMAX, the output image is significantly sharper and has far fewer undesired artifacts. It looks much more similar to the ideal floating point implementation, reflecting the fact that the output SEC is much more consistently close to 1 after optimization, as we saw in the histogram earlier. Next, we provide a quantitative measure of the image quality produced by the GB plus ED circuit with and without COMAX. Here we use the Mean Structural Similarity Index, or MSSIM. This measure has been shown to provide a good benchmark for quantifying how visually similar two images appear to humans. In this graph, the x-axis shows different designs, while the y-axis is the MSSIM, where a higher value is better. Blue bars represent the design without COMAX, while orange bars represent the design with COMAX applied. In addition to the base design, we also evaluated the performance of two existing sequential recorrelation designs, as well as full bitstream regeneration. First, the leftmost pair of bars shows the MSSIM for the circuit before and after applying COMAX in the case where no sequential recorrelation is used at all. As can be seen, the MSSIM increases by a factor of 2.5 times, indicating a massive improvement in the output image quality. Furthermore, the image quality achieved by COMAX by itself produces better results than both of the two sequential recorrelation methods tested, indicated by the fact that the leftmost orange bar is higher than the middle two blue bars. Also, it is possible to combine our method with the use of these existing recorrelators to achieve compounding improvements to the SSIM. When full regeneration is used, combining COMAX with full regeneration provides no additional benefit because full regeneration already achieves the highest possible output SEC. Next, we compare the area cost of all the different designs that were tested. Each circuit was implemented using Verilog code and synthesized in Synopsys using a 45 nanometer cell library. Note that for this graph, a lower value is better. First of all, observe that the circuit design without any recorrelation circuits added has by far the lowest area, at about half the area of the next smallest sequential recorrelator design. Furthermore, applying COMAX actually results in a slight decrease in area. Recall that we just saw COMAX resulted in a factor of 2.5 increase in SSIM, and here we've now shown that the performance increase comes at no additional area cost, highlighting the benefits of COMAX. In conclusion, this work defined the correlation maximization problem and introduced an algorithm called COMAX to solve it in the general case for any given stochastic circuit. We applied COMAX to a representative image processing application and showed that the average output SCC of the first layer increased from 0.72 all the way to 0.97, and that this corresponded to a 2.5 times increase in the measured MSSIM image quality. All of this was achieved without increasing the area or changing the stochastic function that was computed. We therefore recommend that SC designers consider utilizing COMAX, as we've shown it can achieve very favorable performance to area improvements over existing correlation management solutions. That is the end of my presentation. Thank you for listening. Are there any questions? Questions may also be directed to Owen Hoffand at ohoffand@umich.edu.